Let's look at exact equations. Let's start with an example. Let's say 3x times xy minus 2 dx plus x cube plus 2y dy is equal to 0. Let's open up these brackets. 3x square y dx minus 6x dx plus outside the bracket x cube dy plus 2y dy. Try to understand this equation and try to recognize some kind of a pattern. X cube and 3x square y. Okay, let's group them together. 3x square y dx plus x cube dy minus 6x dx plus 2y dy. Okay, if we differentiate x cube y, we get these two, right? 3x square y dx and x cube as it is, then dy. Y is 1. If we differentiate 3x square, we get minus 6x. Okay, similarly, if we differentiate y square, we get 2y dy. Now we can combine all these into a single. Okay, so we get x cube y minus 3x square plus y square. Now, to get the solution, we integrate it. So when we integrate it, this integration and this differential gets cancelled, and we are left with x cube y minus 3x square plus y square is equal to c. So when we integrate it, we have the constant of integration. Now here, if you notice, this integral and differential gets cancelled perfectly. Okay, so that is why we call this as an exact equation, exact differential equation, and we call this exact solution. 3x times xy minus 2 dx plus x cube plus 2y dy is equal to 0. If you look at this, this is a function of x comma y dx, yes, and this is a function of x comma y dy equal to 0. This could be in this form, or if you just take this to the other side, it becomes minus m dx. Bring dx so that it comes down here, then bring back mx, so it could also be in this form, x comma y, m a function of x comma y plus n a function of x comma y dy by dx equal to 0. The definition of an exact equation is the differential equation of the form mxy dx plus n dy is equal to 0, where m and n are functions of x and y, is called exact differential equation if there exists a function, let's say f of x comma y, whose differential df is mdx plus ndy equal to 0. To be more precise, exact differential, or it's also called perfect, whose exact differential df is this. So the way to look at this is, I have an equation of this form. If there is a function whose differential is this, then I can call it as a exact differential equation. Okay, there's a theorem associated with this exact differential equations, and the equation says the necessary and sufficient condition for the equation m dx plus n dy equal to 0 to be exact is dou m by dou y is equal to dou n by dou x. Okay, so again, if you look at it, this condition is necessary for us to call this as a exact equation, or vice versa, right, for looking at it from a sufficiency point of view. Okay, let's actually prove that. So let's look at the necessary part. So we have an equation m dx plus n dy equal to 0, and we have to show that dou m by dou y is equal to dou n by dou x. Only if this is true, then only this will be an exact equation. Okay, now by looking at it itself, we know that it is in exact form, or in a particular form, which we call it as exact. Okay, so the df is going to be m dx plus n dy. That means there is a function whose differential is equal to this. So that function is f. From partial differentiation topic, we know that df is equal to dou f by dou x dx plus dou f by dou y dy. Alright. Now, if we look at the left hand sides, both are df. That means right hand side should also be equal. So m dx plus n dy is equal to dou f by dou x dx plus dou f by dou y dy. Now compare the coefficients. Since equality is there, then coefficients of dx should be equal. So m should be equal to dou f by dou x, and n has to be equal to dou f by dou y. Again, from the session on partial differentiation, we know that dou m by dou y is equal to dou square f by dou y dou x dou y. That means we are partially differentiating m with respect to y. Again, we are going to partially differentiate n with respect to x. We get dou square f by dou y dou x. Now, from the session on partial differentiations, we know that the order in which partial differentiation happens does not matter. So which means dou square f by dou x dou y is equal to dou square f by dou y dou x. And since RHSs are equal, that means left hand sides are also equal. So dou m by dou y is equal to dou n by dou x, right? So that means if it is an exact equation, then this has to be equal. Okay, now let's look at it from sufficiency point of view, from the other side. Let the equation be such that dou m by dou y is equal to dou n by dou x. So we have an equation where this statement is true. Now what we have to do is we have to find a function f of xy. What we have to do is find a function such that df is equal to m dx plus n dy. Okay, to begin with, let's say we do have a function. So let's say we have a function. So let g of x comma y be such that dou g by dou x is equal to m. Now how do we get this g of x comma y? We get g of x comma y by integrating m dx partially with respect to x, keeping y constant. Let's understand the next part carefully. Let's consider dou by dou x of n minus dou g by dou y. Wow. How did this come? Suddenly, I'll come back to this in a little bit. But let's continue for the moment. Now, which means this can be written as dou n by dou x minus dou square g by dou x, no, dou y dou x. Okay. Now, dou n by dou x, this can be written as dou by dou y of dou g by dou x. See, the order doesn't matter, remember? So dou by dou y of dou g by dou x. But we know what is dou g by dou x. Yes, m. Remember here, dou g by dou x equal to m. So what we end up with is dou n by dou x minus dou m by dou y. Now this is equal to 0. Again, how can we say that this is equal to 0? Because we have started off with this statement. Let the equation be such that these two are equal. So if you bring one to the other side, it will be, if you subtract these two, you get 0. Okay, now let's figure out why we are taking this. Remember our equations from the beginning, we are talking of first order, first degree equations, right? So here, if you differentiate a function with respect to y, basically you are treating x as a constant, so all the x's will disappear, which is what we are doing here. Now, how did somebody think of this? I'm sure they would have solved many problems and they might have recognized this pattern. So what all this means is that n minus dou g by dou y is independent of x, because the moment you differentiate it with respect to y, x terms will disappear, which implies that n minus dou g by dou y is a function of y alone. Let's say f of x comma y is equal to, remember we have already started off with such a function g of x comma y, plus to this we add the integral of n minus dou g by dou y. Let's do partial differentiation, right? So when we differentiate, we get d of f is equal to dou g by dou x dx plus dou g by dou y dy plus, now when we differentiate, this integral gets cancelled. So n dy minus dou g by dou y dy. Okay, so now this and this gets cancelled out and we are left with df is equal to dou g by dou x dx plus n dy. Now dou g by dou x is m. So we end up with m dx plus n dy, which is what we started off with. Yes, to prove that if it satisfies this condition, then the equation has to be in this form. Okay, so this itself gives us some idea as to how to solve this type of problems, right? So the first step is to make sure that it is in this form, m dx plus n dy equal to 0 form. Now here it has to be 0, it has to be plus. Second step is to make sure that there is a solution. So verify that it is actually an exact equation. So for that we have to check dou m by dou y is equal to dou n by dou x. If they are equal, then we can go to the next step. We integrate m dx, y equal to constant. So when we integrate this, we get a function. In our proofs and all that, we took it as g of x comma y. Okay, and now integrate n dy, making sure to ignore terms containing x. And the last step is just take the integral of m dx plus integral of n dy, where terms without x, terms of n without x are taken, dy is equal to c. So let's look at that initial example itself. 3x times xy minus 2 dx plus x cube plus 2y dy equal to 0. So if you observe, this is nothing but m and this can be treated as n. So it is in m dx plus n dy equal to 0 form. So m is equal to 3x times xy minus 2 and n is x cube plus 2y. Now we have to verify whether we have an exact solution or not. Now let's say m is equal to 3x square y minus 6x. Okay, now let's say dou m by dou y. This would be what? With respect to y this is. So this would be 3x square. This is dou n by dou x is equal to 3x square. Yes. And if you notice, this is equal to this. So therefore, dou m by dou y is equal to dou n by dou x, which means there is an exact solution. Okay. So now that we know that there is an exact solution, we integrate m dx to get the function for the first part, and then we integrate n excluding terms with x dy equal to, we say, c, a constant. Okay, so m dx, so we have to integrate 3x square y minus 6x dx plus, and here how do we get rid of x? So just ignore it, don't even mention it. So 2y dy equal to c. Now let's integrate it. This would be x cube y, 3x square y minus 3x square plus this would be y square equal to c. So this is our solution. Okay, let's do a few more very quickly and you will realize that it's quite easy. Y times 1 plus 1 by x plus cos y dx plus x plus log x minus x sin y dy is equal to 0. Now if you notice, this is m and this is going to be n. So m is equal to y times 1 plus 1 by x plus cos y, and n would be equal to x plus log x minus x sin y. Let's verify whether there is an exact solution. So dou m by dou y would be equal to 1 plus minus cos y is minus sin y. Dou n by dou x 1 plus 1 by x minus, again we are going to differentiate with respect to x, so minus sin y. Again if you notice, this is equal to this, so therefore this is an exact equation, which means we can find a solution, exact solution. So the exact solution would be, first let's integrate m dx. So we have to integrate y times 1 plus 1 by x plus cos y dx. Y, now here remember we are going to keep y constant. We are integrating with respect to x. Y is constant, so it remains as it is. Now since it is 1, this will be x, because when we differentiate x we get 1, plus log x, when we differentiate we get 1 by x, plus, remember, with respect to x, so x cos y. Now the other part is n, but n has no terms without x. Look at n, this term has x, this term has x, this term also has x. So since there are no terms without x, we can ignore it. So our solution is y times x plus log x plus x cos y equal to c. If you want to verify it, just do a differentiation. Okay, let's look at the next one. This was which one? 2. Let's look at third one. Cos x tan y plus cos x plus y dx plus sin x sec square y plus cos x plus y dy equal to 0. So here m is equal to cos x tan y plus cos x plus y. So dou m we have to verify. Dou m by dou y is equal to, this is cos x sec square y plus cos will be minus, so minus sin x plus y. Okay, n is equal to sin x sec square y plus cos x plus y, and dou n by dou x is, sin is cos, so cos x sec square y plus, again this would be minus sin x plus y. So again this is equal to this. So therefore there is an exact solution. Okay, so to find the solution, integrate m dx keeping y constant. So integral of cos x, let's have square brackets, plus cos x tan y, cos x tan y plus cos x plus y dx. Now this would be sin x tan y plus sin x plus y. Just verify it. If you differentiate this, you should get that. Okay, so sin x tan y plus sin x plus y. Now if you look at n, this term contains x, this term also contains x. So there are no terms in n independent of x. So the solution is, or the function is sin x tan y plus sin x plus y equal to c. Now if there are terms independent of x, just take those terms and integrate them with respect to y and just incorporate that into this equation. Okay, I think that's enough. Bye for now.